Hey, welcome back to another episode. Today I'm joined not by one, but by two beautiful babies. Everybody, what better episode to introduce you to Kaya? Her name is Kaya, and she's a little more shy than Luna, but they are both very good cats. So, welcome. Today is another day where we're going to be practicing mathematics. It is episode 7, technically speaking, but new thing, I'm taking out episode numbers out of these videos because you can watch these in any order, honestly. I'm trying to restructure things. I'm taking some feedback that people have given. So it is technically episode 7. If you want to watch the rest of the series, you'll get a little bit more out of this video. If you watch the other ones, this is a playlist and you can see all of it. But in any case, today we're going to be doing an introduction to logic in more detail. I was going to do a demo on some more induction examples and practice some more induction today. But I think it's better to try to reduce the length of the videos just a slight bit. Please, everybody, let me know in the comments section. By the way, thank you everybody for the comments. I'm listening, I'm reading every single comment, and I want to respond to every single one. Please do leave feedback. Let me know what you would like to see out of this show. So first, I wanted to give some special shout outs to a couple of awesome comments. In particular, this is, if I'm going to be honest, this is my favorite comment recently because I was so happy. Like when I saw this, like I made like a cool little like a puzzle in terms of the last episode that we did, which included the Collatz conjecture. And I encouraged people that you could try practicing on your own. And sometimes these numbers get fairly large. Somebody discovered this incredible fact. So turns out, I didn't know this until relatively recently myself. If you do the Collatz conjecture with 27, that's the first one that is just surprisingly long. It takes 112 numbers in the entire sequence from 27 to 1. And this person did the entire thing, and they discovered it. They had never seen the Collatz conjecture before, and that just made me so happy. And I commented and I asked, like, was it worth it? Did you enjoy it? And they were like, it was worth every minute. And I was like, that's an accomplishment, I think. That's a hell of an accomplishment. So there was that one. Somebody else also wrote a Python script to compute the freaking Collatz numbers, and they tried to verify all the numbers with 6 digits, 5 digits, and 3 digits. Well, 4, 6, and 7, actually. But that's just incredible. Like, for the first 10 to the 6 numbers, it took more than 8 hours. They ran this with a Python script. That's so cool. That is so cool. And yeah, I don't know. Just shout outs to you, Saba94 and Kathy Zega. Congrats. Like, it makes me so happy. And just all in general, these inspirational comments are just, man, like, I cannot believe how many people want to learn math together, like, especially as adults. So special shout outs to Life of Journo and Roger Tripp. It's just incredible to be having some adults on board watching this series and practicing math with me. So, yeah, these are just really inspirational. Please let me know how I'm doing, what you would like to see out of this show so I can make it a good show for you. All right. So one thing about this comment, this person is on the verge of turning 84 and they've been doing math as a hobby, even though they didn't recognize it as a hobby for a few years. They were terrible at math in school. They flunked college algebra, but they passed college level calculus nearly 30 years later, and they were able to ease back into math via an interest and hobby in symbolic logic. Unfortunately, they still use TikTok, but we'll just move on from that. So symbolic logic, I think, really is where a lot of math becomes just super beautiful to me. As a programmer, it's some of the most useful math that I've ever used. So I was really shocked that Lang doesn't do truth tables, whereas everybody else, every other intro to proofs book will always include truth tables. So there is an intro to logic in Lang, and he teaches logic throughout the entire book. I think that today we should do truth tables with our symbolic logic introduction. So we can think of this as practicing logic today. I want to just get a little bit deeper, just like a little more clarity, a little more resolution on the idea of logic and truth tables. So I said, as a SWE, like my path for anyone who doesn't know, I did a bachelor's degree in pure math. Then I worked for 10 years in Silicon Valley companies, including Apple, Google, and Lyft. And now I'm coming back to math, and I'm on a path to try to become a high school teacher, high school or middle school teacher, just because I really, really like teaching a lot. And this is an excellent practice space, I guess. And it's part of the reason why I want these videos to be unedited, one take, and on the longer side. We'll shoot for 30 minutes today, but I don't want to do 10-minute videos because that doesn't feel like I'm really practicing a lecture that I'd be giving to kids. So, yeah, coming back to this, I'm a software engineer, and symbolic logic and complex logical statements are actually just bread and butter. Like, you use them all the time as a software engineer, just all the time. So I think it's important that we do these. All right, so our first bit, let's get into it. The logical connectives. I'm going to define the logical connectives are the functions. I'm going to think of these as functions. And we're going to pronounce these and, or, if, then, and not, or negation. Other words for these are conjunction, disjunction, implication, and negation. So each one of them takes one or two logic statements and returns a new logic statement, which can be evaluated as follows. So a logic statement will be built off of simpler logic statements. A logical statement can either be true or false. It's like a Boolean in programming. A Boolean can either be true or false. Is email valid or something? Is email valid and is user logged in or something? So our two primitives, our Booleans, are A and B, and they can either both be true. One can be true, one can be false. One can be false, one can be true, or both could be false. So there's two options and two variables. So there's two times two possibilities. So we are going to build this truth table for these different logical connectives. Not A. So this one doesn't depend on B at all. So if we just look at the values of A, when A is true, not A is false. And when A is false, not A is true. Okay, so it flips the value from true to false and from false to true. Or depends on both the values of A and B, on A. Yeah, both of them. And it will be true anytime either one of them is true. It could be, both of them can be true, like in the first row. Notice that the first row, both of them are true. In the second row, the A is true and B is false. In the third row, B is true, but A is false. Now, in the last row, both of them are false, so then the or false or false returns false. And behaves this way. You need both of them to be true. You want the only time that the and function returns true is if both sides are true. Otherwise, at least one of them is false. If then, this one is a little interesting. This one is worth thinking about for a second, so I put stars next to it. If then, we should think of this like a promise. If A is true, A implies B says, when A is true, then B is true. If A is true and B is true, then we consider this implication true. The only time that that promise is broken, like A implies B, would be if A is false and B is true. In the third and fourth lines, A is false. A is false, and B can be anything. This is called the vacuous truth implication, and we should think of it like a promise. If A isn't true in the first place, then this promise that when A is true, then B is true, it still holds because A wasn't even true in the first place. It's a little weird to wrap your head around, I feel, the first time, and part of it is that we really want this one to just be telling us if A is true and B is false, then the promise is broken. That one is kind of hard to explain, but you get used to it a bit. And we need it to work that way in order to have examples that we'll see later on. If we didn't define it this way, a lot of math breaks, and I can make that more concrete later. It's just right now it's kind of hard to describe it without some later terminology. So we'll see later that math breaks if you defined it differently. Okay, so next, the connective double arrow, we can pronounce it if and only if, is defined as A implies B and B implies A. So in this case, it behaves just like the symbol shows. We have the forward implication and the reverse implication. Lang has shown several examples like this so far. Like, if 2x equals 5, then x equals 5 halves, and vice versa. If x is 5 halves, then 2x equals 5. That was the example from before. Okay, so it's defined this way. How do we build this? Like, I want to understand what are the values. How do we evaluate this new connective that we're defining based on previous ones? So it's a combination of these two implications. All right, so just like before, we have true and false values for A and B. I'm going to switch to this notation instead. I feel like it's easier to see. It's kind of like a bit mask, or like there are terms for this where we can treat them as true and false, or ones and zeros. I certainly could write ones and zeros everywhere. Personally, I prefer to just leave a blank space if the value is 0, but it's your hobby, dude. You can use whatever notation you want to, I guess. I want to see that this is why are these the values? Why is this how that if and only if operation works? The way it works to see it, though, is that it is true when A and B match. When both A and B have the same value, both of them on or both of them off. both of them true or both of them false. So that's what we want to see, and let's build it. So the way that I want to build this truth table is I'm going to define the if and only if B based on this definition. So I should figure out the values of A implies B, which is right here. So when the only time that it's false is if A is true and B is false. The only time that the implication is false is if false implies true. And so likewise, B implies A is only false when A is false and B is true. B is true, A is false in the third row. Then we want the conjunction of those two. So the and, we want both of them must be true. I can't believe I didn't remember to double check this. 1 second, real quick. Yeah, okay, just double checking. Just double checking something. All right, so here we go. Here's how we're going to do this. If you want, you can use your own helper terms. Like you can define something like let L be this and let R be this. And now I have just some simpler labels to be able to say L and R. So I want to turn on the values when both of those implications are true. So in the first and fourth rows, both of them are true. So now that is the definition of A if and only if B. Either both of them are true or both of them are false. Let's keep going. Next, a tautology. We're going to define something called a tautology. A tautology is a logical statement which is true for every truth assignment of its parts. So no matter what values we assign to A and B, if it's an expression with only using A's and B's and combining those, I mean, of course, we could add C or any other number of terms, but no matter what truth values you assign on the left side of these truth tables, then the evaluation is true in any scenario. So we want to find some examples of logical statements that are always true. For a tautology A, we write this. So we'll call that like the tautology symbol or the double turnstile. Technically, this is a double turnstile symbol. So we want to find some examples of tautologies. And here's everybody's favorite. We're going to start with the law of excluded middle. So the law of excluded middle, LEM, I think it's good to just start out with a couple of examples first. But actually, sorry, very first, okay, I forgot what's underneath that thing. Let's just keep going. All right, so law of excluded middle, let's just go with examples first. One example is the square root of 2 is a rational number, or it's not. Either the square root of 2 is rational, or it is not. There are infinitely many primes, or not. Right? So there are infinitely many primes, or there are not infinitely many primes. And then another stupid example, the cat is alive or not, right? It would be very paradoxical and very strange to think of a cat being alive and not alive at the same time. So there are people who think that we should work in many valued logical systems and things that move away from classical logic and classical two-valued logic. But for thousands of years, mathematicians have worked with two-valued logic. And Enderton, this book that I'm taking a lot of these examples from, points out that the goal is to build a model of logic as a mathematical operations and mathematical system of its own, which mimics mathematical arguments for thousands of years. So we're going to stay with tradition, and it's not the same reason. It's not the same as many valued logic or something, but just so you know, there are some people who reject the law of excluded middle and the idea of proof by counterexample. Some people, or proof by contradiction, I mean to say. Some people find that to be not just inelegant, but there are advantages if you can prove things without using this tautology. But in our system and classically, we consider this a tautology. And so one more time, we want to find a logic statement which is true for every truth assignment of its parts. So what would that be? Now that you've gotten some examples, I wonder if you've thought of it and you found it. It's this on the top right there. A or not A. If A is true, then we have true or false. And then if A is false, then we have false or true. And in either of those cases, this expression evaluates to true. So therefore, the law of excluded middle is a tautology. That either a thing or not the thing. Either a statement is true or the statement is not true. And yeah, now we're done. Okay, so now I'm going to give a bunch of exercises now. And a cool feature, I think, about YouTube is that I can encourage you all to pause the video and try to work these if you want to. I meant to hide this one. Oh, well. Prove the equivalent statement of negative A equals A. What is that? Why does that sound familiar? That was from Lang. Lang N4 was that the negative of a negative is the positive number A. So the equivalent for logic, I wanted you to try to find this yourself, was the double negation is equivalent to the original statement. So if you negate a statement twice, it's the same values. It has the same values as the original statement. Okay, so here's the proof. Here it is right here. A is either true or false. And then that middle column, you can see I built it up to be it's true in either case. And I built this with kind of like helper functions, or like my scratch work is on the right-hand side. But this was my goal. I successfully showed that it's true in both scenarios of the atoms of that expression. Okay, next one. Here's another exercise for you, and please do pause the video if you want to work it and try it. It's okay if not, no judgment. Show that, what is this symbol again? Conjunction. Show that conjunction is associative. So conjunction or and, you could call this, show that and is associative. I haven't written it yet, but in programming, we use this all the time. Oh, I remember earlier, well, yeah, I remember a thing that I wanted to talk about at the beginning, but I'll save it for next time. All right, so show that and is associative. What does that mean again? How does associativity work? Do you remember associativity of numbers, of addition? How did that work again? Associativity of addition says that you can regroup parentheses. That if you have two additions in a row, you can add the first two or the second and third in parentheses first, and then add to the other number. So the equivalent would be in A, B, and C being logical formulas, logical statements. We want to show that this tautology is true. A and parentheses B and C is equivalent to A and B and C. Those two are tautologically equivalent. And here's the proof. Here it is. So this time with three atoms, I forget the name of these. With three propositions, A, B, and C, there are a total of eight total possibilities. In general, if there are n booleans, then there are 2 to the n valuations, right? Like, because every boolean can be either true or false, and you multiply all of those values together. So there are 4 where A is 1, and then there are 4 where A is false. And then within those, there are 2 where B is true, and then 2 where B is false. And then within those, there's 1 where C is true or false. Yeah, okay. So here's the proof table, and this is my solution. I wonder how it compared to yours. Okay. Please do drop a note in the comments if you like your solutions more, or if you have any questions at any point. Please let me know. Yeah. Proof De Morgan's laws. All right, so what are De Morgan's laws? Pause the video. Try it. Do you know what that means? As programmers, we use this one all the time. Just all the time. Yeah, it's very, very, very frequent in like compound if statements that you want to refactor and give new meaningful names. Yeah, this one is very, very useful in the real world. Okay, so De Morgan's laws tells us how negation interacts with conjunction and disjunction. How do the not and operators combine? It turns out that they behave this way. So not A or not B. So notice how the and flips to an or in this De Morgan's law. So and converted to an or in this example, and then likewise in the second, or becomes and. It's kind of like we're distributing the not sign, but notice that the operator flips from and to or. All right. So pause the video if you want to work it yourself. All right. So here's my first solution for the first of the two. I used L and R again to mean the left side and the right side of the equivalence arrows. And then another one here for De Morgan's law. So to take a look at one of these for a second, for example, L, I used L to mean this. So I am able to see that A and B would be true and true, which is true, and then flip from true to false. So this value is false. Likewise, on the right side of that of the first law, we have not A or not B. So not A would be, not A would be 0, or not B, which is 0. False or false is false. So again, we get that value is false. Likewise with all the other ones. You can see A or B on the left would be true, and then A and B would be false. Yeah, all of these, the inner part would be false because all of them have at least one false value. And then when you negate it, then the value is true. So, and then on the right, not A or not B, all of those, not A would flip A to be 0, 0 or 1 is 1, and 1 or 0 is 1, and 1 or 1 is 1. Let's keep going. There's the other proof. Just want to try to describe these for a moment for people who may not have seen these before. Prove this next exercise is a good one. Pause the video if you want to try to work this. And also, what is the name of this? Have you seen this equivalence? So on the left we have an implication, and on the right we wrote it differently. What is the name of this one? It's called contraposition. So this is the contrapositive form of the left. Contrapositive, which is not B implies not A. Oftentimes, to prove a theorem in math that A implies B, it's much easier to prove the contrapositive instead. So here it is. We're going to see this as an exercise. And there it is. Here's my solution for it. All right. So we see that in every case, again, that middle term is true. All right. Next, I'm just going to state a couple of exercises for you all that you can work if you'd like to. Find and prove the two distributive laws for and or. Like, what would that look like? We are looking for something that is like the distributive laws of addition and multiplication. How does multiplication distribute? Like this, right? This time it's going to be, there's two distributive laws connecting. How do and or connect? So think about it. What is the equivalent in logic? And then prove contradiction. This is very related. It's similar. It's quite similar to the tautology of law of excluded middle. In fact, I think that you may be able to see a connection between those two really directly. And now this is a cool one, inspired by fellow math streamer. Shout outs to Math with Ming for hanging out in the chat earlier today. Shout out to Ming. Imagine that this is inspired by a comment he had. Imagine that we don't have vacuous truth. Let's define a new operator squiggle implies. Find one or more tautologies which are no longer tautologies after replacing the implication arrow with squiggle implication. So if we don't have vacuous truth, we would want to fill in some details for people. I feel like maybe I should have written this part. A, B, and then if we define a new operator, A squiggle B, let's just keep ones and zeros here. Then vacuous truth was saying that false implies true. So maybe when the one side is when A is false, then maybe the new value is false. We certainly would want that one to still be true. True, false, false, false. Find one or more tautologies which are no longer true. Which of the tautologies that I've introduced in the rest of the video no longer are always true after, like, if we replaced all the forward arrows with this non-vacuous implication arrow. I'm trying my best. All right. Thank you, everybody. This was fun. This was really fun. mathcanbeahobby.com. If you know anybody who would like to check out these videos, if you know any fellow math geeks who enjoy cats and pure mathematics, that's just a redirecting link to get to the playlist. So discord.jcpractices.com if anybody wants to join and hang out with us there. But the best way that you could give thanks back, honestly, is feedback. Like, I love and thrive on feedback. It's the only way that I can know whether I'm moving in the right direction or the wrong direction with these videos and everything. So if you feel like it, drop a comment in the comment section, or you could go to my feedback survey on Google surveys. feedback.jcpractices.com. And special freaking thanks to all of the channel members and regulars, all the people who are really making this possible. Thank you. I absolutely cannot believe how many people want to study math with me. And Kaya came. She was here for a second. She's so shy. Anyways, thank you again, everybody, for being here and for watching. I hope you have a wonderful day, and I hope you enjoyed. Thanks for watching. Bye. Bye.